In this today's lecture, we'll see how various statistical tests can be used and what are their uses. Now basically, as we know, statistics is the study of uncertainty or study of the population through sample. So many a times it happens that we have very limited data, and on the basis of that limited data we need to draw conclusions about a bigger population, a bigger universe. So how can we generalize these results? And if we generalize, what is the guarantee that these results are going to be correct? There might be some differences which we may miss out. So what are the chances that due to these differences there will be some significant errors or some serious problems with our conclusions? So for studying all these things, we need to develop various tests. So this is the outline of the talk. Firstly, we'll see how to standardize data. Then we'll go for estimation of parameters. Estimation means basically giving some approximate measures which can be used in place of unknown things. And then we would study the sampling distribution of the mean, means how the mean varies from sample to sample. If we change the sample, how that mean is going to change. And then finally, we would provide some confidence intervals for mean. Confidence interval means we'll give some range and we'll assign some probability that okay, most likely my population mean is going to be in this range, and so on. So let's first start with standardization. Now what is standardization? Now when we study something, we have various variables, we have various instruments which record these variables, and so on. So there are different units. For example, if I have data on say heights and weights of individual, then heights might be recorded in say centimeters and weights might be in kilograms. Now if one thing is in centimeters, another thing is in kilogram, then I cannot directly compare these things. So if I want to study some joint thing about these two things, then I need to have a kind of uniform scale where I could compare these things. So for doing such things, it's better to standardize the data. Now what do I mean by standardizing? We basically scale the data and center it around 0. So we make the mean of the data to be 0 and variance 1. As a result, whatever conclusions we draw would be free from the units. Now why is it necessary? Because for example, someone tells me that your suppose before 2 days height of a particular say tree was 10 centimeter and today it is 12 centimeter. So it has grown by 2 centimeter. Now 2 centimeter seems to be a big number. Whereas if I express same thing in meters, then it would become 0.02, and someone may reject saying, oh, 0.02 is a very small thing. But we don't want to base our conclusions on the units. What we want is the actual absolute importance of the thing, and that's why it is better to have 0 mean and unit variance so that things are standardized. Now how do we do this? We already know that data has some mean mu, and we know that expectation is linear. So if we subtract this mean mu, then the mean of the new data would become 0. And another thing that we know about variance is if we have a variable x with variance say sigma square, then variance of ax is a square times sigma square. So using these two properties, for a given random variable x, we define a new random variable z as x minus mu x upon sigma x, where mu x is my mean of the random variable x, sigma x is the standard deviation or square root of variance for the random variable x. Now as we can see, if I compute expectation of z here, it would be 1 by sigma x times expectation of x minus mu x. So it would be 0. And if I compute variance of z, then it would be 1 by sigma square x times variance of x minus mu x. So it would be 1. So now this new random variable z had 0 mean and unit variance, and thus we call that it is in the standard format. So this is known as Z transformation, and it is known as Z transformed random variable. And another reason for doing this stuff is the central limit theorem. Central limit theorem is a famous theorem in statistics which says that if you have this kind of Z transformed data, then under some ideal conditions, this data tends to be a normal distribution. So it behaves more or less like a standard normal distribution. And standard normal distribution is widely studied. Many results are directly available for standard normal distribution. So in such situations, those results can be applied to this data. So Z transformation gives us these two advantages. First is it becomes independent of units. Our conclusions don't depend on unit. And secondly, the results from standard normal data can be used here. Now this is the standard normal curve. So standard normal means this has 0 mean, variance 1, and this is the curve of the probability density. Now as you can see, this is a bell-shaped symmetric curve, and in case of any probability distribution, area under this kind of probability density curve is 1. So the total area under this curve is 1. And if we can see that mu minus 1 sigma to mu plus 1 sigma, this region basically covers 68.26% of the entire area. As we know, entire area is 1 unit. So probability of this region, mu minus 1 sigma to mu plus 1 sigma, is 0.6826. Means this region itself has almost 68% chances. If we slightly increase our region on both the sides, if we consider say mu minus 2 sigma to mu plus 2 sigma, then it covers 95.46% of the entire population. It means that out of say 100 people, if suppose we are recording marks of 100 people, then around 95 people would have marks in the range mu minus 2 sigma to mu plus 2 sigma if their distribution is assumed to be normal. And similarly, if we go a bit further to mu minus 3 sigma to mu plus 3 sigma, then the area covered is almost 1. It's 99.73%. Means even though the range of the normal distribution is minus infinity to plus infinity, which is a very huge thing, in this finite range mu minus 3 sigma to mu plus 3 sigma, we are getting 99.73% of observations. So it's enough to study these things. The chances of getting observation less than mu minus 3 sigma or greater than mu plus 3 sigma are very small. And these are also known as 6 sigma limits in quality control. Some of you may have heard about Mumbai Dabbawalas. So the probability of making error in their case turned out to be very small, and that's why they were said to be 6 sigma compliant. So this is the basis of quality control. And now we are going to use this curve to study sampling distribution of the mean and then to draw some conclusions about the population on the basis of the sample. Now for doing that, we need to first find population parameters. Now what are population parameters? Parameters are the things that give us information about the population. So if I have some population, for example say trees in the entire world, and suppose I want to study their height, then the parameter might be say average height of a tree, then minimum height or maximum height, something like that. Now the problem is I cannot go on measuring heights of trees in entire world. I have limited resources, I don't have much time, I don't have much money, and so on. So I cannot get information about all the trees, so I cannot compute the population mean. Now what to do in such situations? Then comes the sampling. So in such things we draw a sample and then base our conclusions on that sample. So sample means we would select some small area and then we would measure heights of trees in that area, and in recording that data we would compute its mean, and we would say that okay, it might give me at least a rough idea about what the population mean is going to be. Obviously it won't give me the exact value, but still it will give me an estimate. Thus we use things from sample, which are called as sample statistics, to estimate population parameters which cannot be computed directly. For example, if we want to compute population mean, then for that a reasonable estimate would be a sample mean. Now this kind of sampling we usually see when we go to a doctor. When he wants to test our blood for possibility of some disease or something like that, he doesn't extract entire blood because it's not possible. You can't live. But then he takes a small sample of blood and then he performs the test on that sample and gives us the conclusion. So this is also one form of sampling. So after sampling we get sample mean as an estimate for population mean, and then if we are interested in studying spread of the population, then we would need population standard deviation or population variance. For that we can compute what is known as sample variance. So sample variance is given here by S square. It is this formula. So we know that population variance is basically expectation of squared deviations of the observation from the mean, from the population mean. So we just take its sample version. Because it is expectation, we kind of take mean here, and mean of what? Mean of squared deviations from the mean. So here we don't know population mean, so that is replaced by its estimate, sample mean. So we are taking xi, means the ith observation, minus x bar whole square. And then these estimators have some good properties in a sense that sample mean is unbiased for population mean. Now what do I mean by unbiased? Unbiased means if I take expectation of the sample means, then it is same as the population mean. Now what do I mean by this? I have the entire population. If suppose I draw all the possible samples from that population, compute sample mean of each sample, and if I take mean of all these means, then that mean turns out to be same as the original population mean. So this is same as saying that sample mean is unbiased for population mean. And similarly, sample variance is unbiased for population variance. And to get this unbiasedness, we basically have n minus 1 here in the denominator instead of n. Otherwise we could do it with n also, but then it doesn't remain unbiased, and so if we want unbiasedness, we take n minus 1. So now we know that even though we don't know the population parameters, we can get some idea about them through sample statistics, and these sample statistics have some good properties in a sense that in a large sample they will be more or less closer to the population parameters. Now the thing is, suppose I get some sample, I get its sample mean, another person may get some other sample, so obviously his sample mean is going to be different than my sample mean. So whose answer is correct? Are we both correct? Are we both wrong? Or what? So for that we need to study the sampling distribution of the means. Means if we have say more than one sample, if we have say hundreds of samples, then how the mean of these samples are going to behave. And in most of the ideal setups, in IID situation, means if my observations come from identical distribution and if they are independent, then the sampling distribution of the mean turns out to be normal, and mean of this distribution, as we know because of unbiasedness, will be same as population mean. So this is basically the distribution of the sample means if we draw a large number of samples. And then we know about the mean. Okay, mean of all these sample means is going to be population mean. But then how far away these means will be from each other? Suppose in one sample I get mean say 0.1 and in another sample suppose I get mean 10. Then does it make any sense? Is it actually coming from same population or so on? So for measuring this spread, we need to have some estimate about the spread of the means. So that is known as standard error of the mean. So standard error of the mean is a way of expressing variability of sample means. So what it does is, it describes uncertainty about how well the mean of a sample is, means how correctly it approximates the population mean. And it is basically standard deviation of the sampling distribution. Means if I plot the graph of many sample means, then I can compute the standard error through the spread of that graph. And formula for computing this thing is sigma x upon root n. Now my sigma x is the original standard deviation of the original data, and because I know that my sample mean x bar is 1 upon n summation xi, so I get that variance of this x bar would be sigma square upon n by the linear properties of the variances. And so standard deviation would be sigma upon root n. So this is known as standard error. But then again there is the same problem. I don't know this sigma because this is a population variance. So I cannot actually compute this standard error. So I need to estimate this standard error. So same thing, replace sigma by its estimate. So replace population standard deviation by the sample standard deviation, and that will give us estimate of the standard error of the mean. And now, once I have information about the mean and distribution of the sample mean, then that we can use for constructing confidence intervals using the graph that we saw earlier. So we know that if things are normal, then within mu minus 1 sigma to mu plus 1 sigma, there are 68% observations. So, because of the fact that mean of the distribution of sampling means is population mean, there is 68% chance that the population mean lies within one standard error of the sample mean. Similarly, but now if I want to be 100% sure, then what would I want to do? Now the problem is, we know that range of the normal distribution is minus infinity to plus infinity. So if I want to be 100% confidence, then I would have to give entire real line. Now which doesn't make any sense. It means that I am not using the information that I got from the sample. So what we do is, we try to be 95% sure. So how can we get a 95% confidence interval? So we first need to find that point in the normal curve which would give me a 95% interval. So that corresponds to 97.5th percentile of the curve, and from the downside it is 2.5th percentile. So percentiles are basically observations which divide the data into 100 equal parts. So if I mark 2.5th percentile, then it means that to the left of that point I have 2.5% observations, and to the right of that point I have all the remaining, means 97.5% observations. Similarly, if I mark 97.5th percentiles, then to the right of that I would have only 2.5% observation, to the left I would have 97.5%. So if I consider area between 2.5% percentile and 97.5th percentile, then it means that 95% observations are between these 2 points. So that can become my 95% confidence interval. And this 97.5th percentile for standard normal curve is almost 1.96. So if we want a 95% confidence interval, then it is given by x bar minus 1.96 into standard error, that is s upon root n, to x bar plus 1.96 s upon root n. Thus, we are 95% sure that my population mean mu lies in this. What does it mean? Now this means that if suppose I draw a large number of samples, for example say 10,000 samples, then almost 95% of the times, means almost 9,500 times, my population mean will be in the intervals of this type. Similarly, if I want to extend my confidence level a bit, I may want to be say 99% confidence, then I would have to use 99.5th percentile. So it is 2.575. So this is 99% confidence interval for population mean. Here is a graph to represent the same. You can see this is a standard normal curve. So on the left, if I mark minus 1.96, then shaded area just represents 2.5 portion, and again to the right of 1.96 also I have only 2.5% area, and I know total area is 1. So in between minus 1.96 to 1.96 we have 95% area. So this is the representation of the same thing in the graph. Now there is another approach for doing same thing. Instead of actually computing confidence interval, we may compute something known as Z statistic. Now what is a Z statistic and why do we use it? We are going to use it to test if my population mean has some value which I expect. For example, if some company claims that their toothpastes are they are 50 gram toothpaste they are selling, and if you feel that okay, it's not 50 gram, I purchased it many times and I computed the weights, it's always less than 50 grams, and if I want to sue that company, then what I want to do is statistically I would have to prove that their population mean is less than 50, whereas claim of that company would be no, our mean is 50. So their hypothesis would be mu equal to 50, and we would have to prove that it is wrong. We would have to prove that mu is less than 50. For doing such business, we need to construct what is known as this Z statistic. So this is the formula for Z statistic. It's x bar minus mu upon sigma by root n, and then this Z follows standard normal distribution. So it is normal 0, 1. And then the conclusion is based on the fact, it's based on some probability. And what probability? That how likely is it to get a value of Z which is say very large or very small, something like that. Means if my population mean is 50 and suppose I get sample mean as say 45, then what are the chances of getting such a bad sample if my population mean is actually 50? If those chances are very less, then I can say that no, it means that there is something wrong, population mean is not 50, and that's why I am getting a sample having such a small sample mean. Here is one example. So average zinc concentration recovered from a sample of zinc measurements in 36 different locations is found to be 2.6 grams per millimeter. So we have to construct 95% and 99% confidence interval for the mean zinc concentration in that river. So what we have a sample of size 36 and we know the sample mean, which is 2.6. So on the basis of this sample of size 36, we need to give a 95% confidence interval for population mean, and again a 99% confidence interval for the population mean, and population standard deviation is assumed to be known and it is given to be 0.3. So this is the notational representation of our data. X bar is 2.6, sigma is 0.3, and n, the sample size, is 36. We know that 95% confidence interval is x bar minus 1.96 into sigma by root n, and upper end point is x bar plus 1.96 into sigma by root n. So substituting the values of x bar, sigma and n, we get that mu is between 2.5 to 2.7. How do we interpret this? So we are 95% confident that the population mean is between 2.5 to 2.7 and our sample mean is 2.6. Means basically we are 95% confident that the sample mean differs from the true population mean by amount which is less than 0.1, because the interval is of, if we see the length of the interval, the total length is 0.2. So one side is 0.1. Now this thing can also be used for sample size determination. So if we are using x bar to estimate mu, then we need to be certain about the reliability of the x bar. We need to be a bit sure how much correct our estimate is going to be. So we want to be 100 into 1 minus alpha % confident that our error is very small, and that error is, say, that error would be z alpha by 2 sigma by root n. This alpha and alpha by 2 business is again from the percentile thing. We know if we want to be 95% sure, then we take correspondingly 95th percentile and so on. So this is similar to that. So how large sample is necessary to ensure that error in estimating mu is less than the specified amount E? Suppose someone tells me that okay, I want error to be less than, say, 0.1. Then to be so much sure to give such an accurate estimate, I would obviously need a large sample. So large means how large? So for computing that, we can use the same thing. Reverting the formula of confidence interval that we have, we would get n to be z alpha by 2 sigma upon E whole square. So if my sample size n is computed using this formula, or if it is greater than this n, then I can be 100 into 1 minus alpha % sure that error won't exceed E, error in estimating my population mean using sample mean. So in case of zinc concentration thing, if we want to be, say, 95% confident that our estimate of mu is wrong by less than 0.05, then the sample size turns out to be 138. So see, there with the sample of size 36, the error was 0.1, and now we want the error to be still less. So we want error to be 0.05. Then obviously we would need a larger sample because we want to be more sure about the things. Now similarly, from the formula here you can see that sigma is in the numerator and E is in the denominator. So if I increase sigma, then my n is going to increase. Means if the variation in the data is more, then obviously I would need a larger sample size. Now if the variation is more, then for that sample to be a representative of the population, it needs to have more points from the population to capture whatever variation is there. So more variation implies that I need to have a larger sample size. And similarly, you can see that E is in the denominator. E is the error. So if I want to reduce the error, means if I decrease E, then also n is going to increase. So if I want to reduce the error, then obviously I need to have a larger sample to be more confident about the things. So you can see that n is inversely proportional to E and n is directly proportional to sigma. So if we want to determine the sample size, then we need to have these two things fixed in our mind. So today we'll stop here. Thank you. So today we are going to see a few statistical tests and the situations in which these tests can be used. So here is an outline. Firstly, we will define what do we mean by hypothesis testing, what is hypothesis and what do we mean by testing that hypothesis. Then we would study some one sample tests, z-test and t-test, and then we would have two sample tests, and there are two types of two sample tests, paired tests and independent sample tests. So what is a hypothesis? Before we start with any research, we need to have some assumptions. We need to state something which we are going to test. So there is something known as research hypothesis, which is the thing that we are interested in. So basically, we want to conclude something about that research hypothesis. And then there is another thing which is known as null hypothesis. Hypothesis of research hypothesis. For example, if I want to claim that average height of the trees in my garden is say 3.5 feet, it's greater than 3.5 feet, then that becomes my research hypothesis. I want to claim that average height of the trees in my garden is greater than 3.5 feet. And my null hypothesis is the negation of research hypothesis. So null hypothesis would mean that average height of my trees is equal to 3.5. It is not greater than 3.5. And then, because these hypotheses are negation of each other, if null hypothesis is true, then research hypothesis is false. And if research hypothesis is true, then null hypothesis is wrong. And this research hypothesis is commonly known as alternative hypothesis in the statistics. So this null hypothesis is denoted by H0 and alternative or research hypothesis is denoted by H1. So these are the common terminologies: reject H0, accept H0, or reject H1, accept H1, something like that. And now, why do we do such tests? The thing is, one can never prove a generalization. For example, suppose I want to prove that all swans are white. How do I prove this? I'll have to see each and every swan in this world and then record that it is white and so on. But then this is a very time consuming task. I may not get all the swans. So even if I say have 100 swans and claim that 100 are white and prove that 100 are white, I still cannot claim that all of them are white. Someone may still come up with one swan which is not white and my entire efforts will go into waste. Whereas disproving things is easier. So suppose I want to disprove this, that all swans are white, it's enough to produce one black swan. I don't need to go on finding all the swans. As soon as I get one black swan, I can stop there. So disproving is always easier than proving things. And that's why instead of proving research hypothesis is true, we basically try to disprove the null hypothesis. So we try to get some evidence against the null hypothesis and which concludes that our research hypothesis is more likely to be true than the null hypothesis. So this is the basic principle in testing of hypothesis. Now here is an illustration. Suppose my null hypothesis is average weight of the fish obtained per week is less than 40 tons. And H1 or alternative hypothesis is average weight of fish obtained per week is more than 40 tons. Now when would I have this situation? For example, someone wants to go into fishing business, but other person has told him that if you get at least 40 tons of fish every week, then only this is going to be beneficial. So he needs to study if it is actually possible to get average weight of fish greater than 40 tons in most of the cases, in most of the weeks. Then only this thing is going to be feasible. So what do? We first frame the null and alternative hypothesis, which we have already done. Then we collect the appropriate data. Then we compute the test statistic, decide some level of significance alpha. Now how do we decide level of significance alpha? We have to decide what confidence we want to have. So if confidence level is 1 minus alpha, then level of significance is alpha. Means if I want to be 95% sure about my conclusions, then I would take my alpha to be 1 minus 0.95, so it would be 0.05. and then we have to decide whether to accept or reject H0 on the basis of the value of the test statistic. Now there are null hypothesis. For example, I want to test null hypothesis mu equal to mu naught, that my population mean takes some specified value mu naught. Then there are two types of alternative hypothesis. One is known as one-tailed, another is known as two-tailed. So what is one-tailed alternative hypothesis? It can be either say mu is greater than mu naught or mu is less than mu naught. Because we know that H1 is negation of H0, so basically we want to say mu naught equal to mu naught, but only in one direction. So we would either say mu is greater than mu naught or mu less than mu naught. And two-tailed is simple negation, so mu not equal to mu naught. So we have to also decide whether we are interested in one-tailed H1 or two-tailed H1. Next thing is to find out the criteria for deciding whether to accept or reject H0. So what we do is we find the probability of the test statistic value if the null hypothesis was true, which is also known as p-value. So we compute conditional probability that if my null hypothesis is true, then what are the chances of getting the value of the test statistic that I have obtained now, or more extreme than that. So it can be something like probability of t greater than or equal to t calculated, and if this p-value is less than alpha, which was my level of significance, then we reject H0. Another way of doing the same thing is to compare the obtained value with the threshold value. Threshold value is denoted here by t tab, which is also known as tabulated value. So threshold value is computed in such a way that probability of t greater than t tab would be alpha, means that probability of getting a test statistic larger than the threshold value is alpha, which is say 0.05. So it's very small under H0. So if my calculated value turns out to be larger than the threshold value, then in such situations we are going to reject H0. Here is the graphical representation of the same. Suppose my t tab and t cal are as shown in picture. Then we know that t tab is basically such value to the right of which I have 5% area, suppose. Then because t cal is to the right of t tab, the dark area would be less than 5%. It is a subset of the original shaded area. So it is less than 5%. And my p-value is the probability of this dark area. So it's going to be less than 0.05. So this is a typical situation in which case we are going to reject H0. So, but then we always said that we are not 100% sure. We can either be say 95% sure or 99% sure and so on. So obviously there are chances that we are going to commit some errors. So what are those errors? So there are two types of errors involved. First type error is reject H0 when it is actually true, means wrongly rejecting H0. And second type of error is accepting H0 when it is actually false. So it is wrongly accepting H0. They are also known as producer's risk and consumer's risk because of their interpretation. For example, if we have example of the toothpaste thing, then if my H0 is that the actual mean weight of the toothpaste is say 50 gram, and if I reject H0 when it is true, means if I prove that average weight is less than 50 even though it was actually 50, then producer is at loss. So it is producer's risk. And reversely, suppose that average weight is actually less than 50 but my sample supports that it is equal to 50, then it is consumer's loss. So it is also known as type 2 error is known as consumer's risk. And probability of the type 1 error is same as our level of significance alpha, And probability of type 2 error, if suppose we denote by beta, then power of the test is 1 minus beta. Now we know type 2 error is basically accepting H0 when it is false. So complement of this would be rejecting H0 when it is actually false. So it is basically probability of a correct rejection. So it is known as power of the test. How much powerful is the test means how many times can it correctly reject the null hypothesis. So we generally try to have maximum power when we try to maintain this type 1 error below alpha. Now let's go to the first one sample test, which is known as Z-test. Now Z-test here we are using for testing the hypothesis mu equal to mu naught against either say mu not equal to mu naught or mu greater than mu naught or mu less than mu naught. We have to choose one alternative out of these three. The test statistic is defined as this. It is x bar minus mu naught upon sigma by root n, and this test statistic has normal 0 1 distribution, means standard normal distribution under H0. Means if mu is equal to mu naught, then this quantity Z follows normal distribution. Now rejection criteria would be different depending on our alternative hypothesis. If suppose we are testing for mu equal to mu naught against mu not equal to mu naught, means if my alternative hypothesis is two-tailed, then it means that I would be rejecting values of Z which are very small as well as those values which are very large. Means my rejection region is on both the sides because I have two-tailed H1. So my rejection criteria would be mod Z greater than Z alpha by 2. So if I have too small a value, I would reject. If I have too large a value, then also I would reject. If suppose my H1 is one-tailed, means if suppose I have mu greater than mu naught, then in such situations, it means that my H1 says that population mean has to be greater than mu naught. So my region favorable to H1 would be Z greater than Z alpha. So I have only one-tailed critical region. So if my test statistic value turns out to be very large, then only I can safely claim that mu is greater than mu naught. And exactly on the parallel lines, if I want to test mu equal to mu naught against mu less than mu naught, then I would be rejecting H0 or I would be accepting H1 if value of my test statistic is very small. So if Z is greater than minus Z alpha. And what are these Z alphas? These are basically alpha percentiles of the standard normal distributions. So in the first thing we take Z alpha by 2 because we want total critical region to have probability alpha. So on the left hand side it would have probability alpha by 2, and on the right hand side also the critical region would be of probability alpha by 2. Whereas in the remaining two cases we have only one-sided critical region, so entire probability alpha is on one side. That's why we take Z alpha and not Z alpha by 2. And suppose we want to compute p values, then how do we compute? Again there are three things. If my H1 is mu not equal to mu naught, then I will have to compute probabilities on both the sides. So I would compute probability that Z is greater than mod Z plus probability that Z is less than minus mod Z under H0. Similarly, for mu greater than mu naught, we would have probability of Z greater than Z, and for mu less than mu naught, we would have probability Z less than Z. So suppose I want to test that mu is less than mu naught, then what we would do is, how likely is it to get such a small value of the test statistic if my H0 was actually true, and if this thing has very small probability, then my H0 is likely to be false, so we reject H0. But then we cannot apply this kind of test to every data. This thing has to follow, the data has to follow some standard properties, then only we can apply these tests. So these are assumptions for the test. Firstly, data has to come from a normal population. Secondly, population variance should be known. So the data should be from a normal population, means it should be more or less symmetric and mesokurtic and so on. So the normality assumption can be tested by using various normality tests which are given in the literature. And second thing is population variance should be known. And many a times if you have average sample with say greater than 30 size, then it tends to be normal. So normality assumption is generally valid if your sample size is greater than 30, unless your data is extremely skewed or something. Next thing is t-test. Now why do we need another test? The thing is, we may not know the population variance. Sometimes even the population variance is unknown. So in such situation, I cannot use z-test because we have an assumption of known population variance for z-test. So we need to have something else. So there is a t-test. Now test statistic for t-test is almost similar to test statistic for z-test. The only difference is sigma or the population variance is now unknown. So it is replaced by its estimate S. Other things are exactly same. So the new test statistic is x bar minus mu naught upon S upon root n, and it follows t distribution with n minus 1 degrees of freedom under h naught. So tabulated values for this t distributions are available in the statistical tables, and we can use those tabulated values to compute the rejection criteria. So for example, again we have three types of alternative hypothesis. So if we have mu not equal to mu naught, then we would reject if modulus of t cal is greater than t alpha by 2 n minus 1. Now this is exactly parallel to z thing. Because we have two-tailed critical region, we are considering alpha by 2 percentile because we want to leave out alpha by 2 region on left hand side as well as right hand side, so that total left out region or total critical region is alpha, is having probability alpha. Similarly, in case of one-tailed test, we would have entire critical region on one side, so we would use alpha percentile. So we would reject h naught in favor of h1 mu 1 greater than mu naught if my t cal is greater than t alpha with n minus 1 degrees of freedom, and if my h1 is mu less than mu naught, then we would reject h naught if t cal is less than minus of t alpha n minus 1. So it is again exactly same. If I am interested in mu greater than mu naught, then I would be rejecting h naught if I get a very large value of the test statistic, because that large value is going to be less likely under h naught. And if we want to compute p values, then again it is exactly same. We would compute probability of t greater than mod t cal plus probability of t less than minus mod t cal, and same thing for one-tailed tests. But then there are some assumptions for t-test also. Again, data has to come from normal population, population variance is unknown, and this t-test is generally used for small samples. The thing is, due to central limit theorem, if we have a large sample, then degree of freedom for the t would be large, and in such situation t distribution tends to the normal distribution. So if we have large sample, then we can use z cutoff points directly. So in such cases, t-test and z-test won't be much different. So t-test is generally used for small samples. For large samples, one goes for z-test. Now what if we want to compare two samples? Until now what we did was testing for mu equal to mu naught. Means we tested that mu has some specific value mu naught. But I might be interested in testing the hypothesis mu 1 equal to mu 2. Means suppose I have two samples and I want to test if their means are equal. For example, we have two classes and we want to see if average intelligence level in both the classes is same or not. So in such situations, our null hypothesis would be mu 1 equal to mu 2. Now here, let's first go for independent samples. just like as I said in case of two classes. The two classes are independent. So T calculated would be x1 bar minus x2 bar upon standard error. And as you can see, if mu1 is equal to mu2, then means under h0, mu1 minus mu2 is 0. So under h0, expectation of this quantity is 0. And standard error is computed using the formula given here. It is square root of s square p into 1 upon n1 plus 1 upon n2. So what are n1 n2? n1 n2 are basically sample sizes. n1 is sample size for first population whose mean is mu1, and x1 bar is corresponding sample mean, and n2 is sample size for population 2 whose mean is mu2 and corresponding sample mean is x2 bar. And s square p is known as pooled variance. So it is computed by using the formula given there. It's a kind of weighted average of the two variances. So it is computed by using this. And then this test statistic follows T distribution with n1 plus n2 minus 2 degrees of freedom. So we can use T tables to compute the cutoff points. And then we may not have independent samples always. For example, I want to test if a drug is effective. I have some patient, say psychiatric patients, and we want to give them some drug and see if their hyperactivity is reduced or not. So in such case, my first sample would be their scores on hyperactivity test before administering the drug, and my second sample would be their scores after administering the drug. And I am interested in testing whether the average score before administering the test is same as average score after administering the test. Now here the problem is the things are related. I am testing the same patients. So suppose a person has very high score before the test, then obviously after the test his score is again going to be higher compared to other patient. It won't be drastically reduced. So I cannot treat these samples to be independent. So my observations are basically paired. My x1 needs to be compared with y1. I cannot compare before test score of one person to the after test score of another person. I have to maintain that paired relationship. So we have to apply what is known as paired t-test. Now how do we do that? So instead of simply computing x bar and y bar and taking their difference, what we do is we first compute difference for each observation. So we compute quantity di, which is difference in the after test score and before test score for each observation. So basically di is xi minus yi. And then hypothesis of interest we know is mu1 equal to mu2. It can be translated as mu d equal to 0. That mean of the difference is 0. Because if there is no difference, it means mean of the difference is 0. And so our test statistic becomes d bar upon standard error of d bar, and it follows again t distribution with n minus 1 degrees of freedom. Now as you can note, here we had different sample sizes n1 and n2. We cannot have different sample sizes here because we have paired samples. So obviously if I had n patients before, I am going to have n patients after. So I have only one n, and hence degrees of freedom are also n minus 1. So these are the tests which can be used for testing means and which can be used for drawing conclusions about the populations on the basis of sample. So we'll stop here. Thank you.